The process of cooling neutral atoms or molecules through laser interaction with the atoms is known as laser cooling. In this case, cooling represents atoms moving slowly, trapping them in a certain region. Various techniques for laser cooling have been developed. Laser cooling may be used for high-resolution spectroscopic measurements such as those for frequency standards of optical clocks, highly accurate measurements of the gravitational field, and studies on quantum effects such as Bose-Einstein condensation. In this lecture, we will introduce fundamental concepts of some representative laser cooling techniques. Here we can see three portions. They won the Nobel Prize in Physics in 1997 for laser cooling. Especially Stephen Chu served as U.S. Secretary of Energy from 2009 to 2013 under the President Obama administration. Now let's see first the Doppler cooling. Laser cooling is a technique for trapping neutral gas atoms or molecules in a specific area. So laser cooling is a technique for trapping neutral gas atoms or neutral molecules in a specific area. Electric and magnetic fields easily trap the charged particles. In contrast, neutral particles are unaffected by an electric or magnetic field. Instead, neutral atoms were able to slow down and eventually cool down as a result of the laser cooling. In 1975, Hensch and Sherlock suggested that neutral atoms can be cooled using laser beam in opposite directions with a little red-shifted laser beam in comparison to the natural frequency of atoms to be cooled. The red-shifted laser beam should be used to match the natural frequency of the atoms, since moving atoms see the laser beam as being blue-shifted. We'll explain later. Due to the collision with photons brought on by momentum change of this much, thus the temperature of the atoms falls. The atoms acquire momentum, this momentum, when it interacts with the laser beam with the angular frequency omega, and corresponding energy, for example, sodium atom, we can calculate energy equal p squared over 2m, and this is momentum change, so we can put this here, and we can have the 10 to the minus 10 electron volt energy change, so we can get the temperature or microkelvin. That is called the single photon record temperature unit. Now let's see this figure. The laser beam has frequency omega, and mass of atom is m, and atom is moving in opposite direction of laser. Then omega 0 equal atomic resonance frequency. So this atom will see the laser beam with frequency omega as this frequency due to the Doppler shift, because the atom is moving toward the laser, so we have the plus here. So this atom will see the laser beam with a little larger frequency. For compensator, this one, we can write this in the in terms of wavelengths. So lambda 0 corresponds to the atomic resonance frequency. So lambda is the wavelength of the laser beam. So to match the resonance frequency of the atom, we have to supply a little shifted laser beam. So since here rather shifted laser beam should be used to match the natural frequency of the atom, since the moving atom see the laser beam as being blue shifted. So we have to use the laser light with laser shifted to match the atomic resonance frequency. If an atom observes a photon from a laser beam, it will experience a change in momentum in the laser beam's direction. That is opposite of the atom's moving direction, then which will reduce the atom speed and thus lower its temperature. Okay. So laser is moving in this direction, and the atom moving in opposite direction. Due to interaction with the laser or with the atom's momentum will be increased in this direction, right? Because laser beam is in this direction, okay? And the speed of atom is in this direction. Speed of the atom will be reduced, so that corresponds to the temperature decrease. Okay. However, when atom observe the photon, then atom will move to the excited state, and the atoms in this excited state will move to the ground state, emitting light photon. Okay. So when an excited atom releases a photon to move from the excited state to the ground state, it will recoil in the opposite direction of the photon that was released. So when atom released photon in this direction, then atom will recoil to opposite direction, right? Okay. Then the average change the momentum caused by the coil will be zero, since the direction of the atom's recoil is random. So all direction. So atom will release the photons all direction. So the direction of a recoil of the atom are also random. So every change in momentum caused by recoil will be zero. So we don't have to consider that recoil effect. As a result, we can expect that the atom's overall temperature will decrease as a result of their interaction with the laser beam photons. So that means atom's speed will be reduced. So that corresponds to the temperature decrease. Okay. So if we use a pair of lasers pointing in opposite directions, so atoms here, and we use a pair of laser in opposite directions. One laser slows down atoms moving in one direction. So this laser reduces the speed of atoms in this direction, and this the other direction. So one laser slows down atoms moving in one direction, while the other laser slows down atoms moving in opposite direction. So thus atoms will trapped in some position. Okay, it cannot move to this direction. Also, it cannot move to the direction due to pair of the laser light. Okay. Thus, three pairs of orthogonal lasers can slow down atoms in three dimensions. So there's one dimension. So if we use a pair of three laser light, then we can trap the neutral atoms in a certain positions. Okay, so that corresponds to the decrease of temperature of the atom. Atoms generated by an oven move at the speed of roughly 1000 meters per second. The number of atoms with natural frequencies that match the frequency of the laser beam is limited if the laser beam used for the polar cooling has a fixed frequency. So if we use laser with a fixed frequency, then some of atoms will interact with this laser. Okay. Furthermore, since the frequency of the laser beam is fixed, while the speed of the atom is reduced, okay, by their collision with the laser beam and photons, the resonance requirements for atoms to observe the laser beam photons is not satisfied. Therefore, the Doppler cooling approach cannot be used to cool the atoms. Due to the atom's decreasing speed, we must continuously satisfy the altering resonance condition in order to cool them. In 1978, Letkov raised the laser beam's frequency gradually from low to match the atom's altering resonance frequency caused by decrease in speed. So that is angular frequency of laser light, and omega 0 is the natural frequency of atoms, and the physical speed of atom if the speed of atom is decreased, then we have to use the laser light with higher frequency. Okay, so that cope with the laser beam's frequency gradually from low to match the atom's altering resonant frequency caused by decrease in speed. So the atom's speed is decreasing, then we have to use laser light with a higher frequency. So he raised the laser beam's frequency to match the atoms decreasing atoms resonance frequency with a decreasing speed. The fastest atoms are initially cooled by being resonated by low frequency laser beam. Okay. Following that, the increasing frequency of the laser beam satisfies the resonance condition of the atoms with a decreasing speed, as seen in this equation, resulting in a drop in temperature. In 1975, Chu et al. Decreased the speed of natrium atoms to 60 centimeters per second, which corresponds to a temperature of 290 microkelvin. Now let's see the subdoppler cooling. Phillips used the magnetic field to alter the energy levels of atoms by Zeeman splitting. In 1981, in order to satisfy the resonance requirement, instead of adjusting the resonance frequency of decreasing speed atoms by changing the laser frequency. In this method, the atomic beam travels through the decreasing magnetic field. Atoms follow this path and collide with laser photons to slow down their speed. In addition, as the magnetic field decreases, the Zeeman splitting between the excited and the ground levels drops. As a result, the reduction in Zeeman splitting balances the decrease in resonance frequency caused by atoms slowing down. The magneto-optic trap is the name of this device. Phillips cooled natrium atoms to 43 microkelvin in 1988 using the Mott apparatus, which was significantly lower than the Doppler cooling limit of 240 microkelvin. This figure shows the Mott optical trap. The center of the trap is targeted by three pairs of opposite propagating mutually orthogonal circular polarization laser beams. So that this position is the target of atomic atom trap, and we have three pairs of the mutually orthogonal circular polarization laser beams. This trap center, the center here, is located at the zero of the quadruple magnetic field produced by two coils, anti-Helmholtz coil, that have opposing currents. So these two coil forms the anti-Helmholtz coil. The current direction here is this direction, and current of this coil is the other direction. And then by these coils, magnetic field is produced in this way. How the atoms are trapped in the z-axis is depicted in the energy level diagram below. This diagram. The resonant laser causes the atoms transition from a ground state with zero angular momentum z equals 0 to an excited state with angular momentum z equals 1. So they equal 0 energy level and z equals 1 energy level. Now we consider two-level system. The excited atom can exist at the three magnetic sublevels mj goes -1, 0, +1 respectively in a magnetic field. Also in a magnetic field, the energy levels are splitted, J1 splitting. We have three sublevels for j equals 1, mj equals 0, mj equals +1, mj equals -1. We have three sublevels. mj equals 0 or no difference in the magnetic field, but mj equals 1 field is changing by this direction, mj equals -1 change this direction, and field equals 0 at the center, and as we go in this direction, the field strength is increasing. Also for this direction, field strength is increasing. So by J1 splitting, energy levels are changing in this way. mj equals 1, mj equals -1, changing in this direction. Okay. And the laser frequency we used is this one, this level. So resonant condition is met here. Okay. So there's this center. So there is targeted position of atom trap. The magnetic field along the z-axis has the form linear form KBZ, KZ. So as a result, J1 shifts occurs linearly in the mj equals -1 and mj equals +1 sublevels. No change if mj equals 0. Circular polarized laser beams with the same helicity are propagating in the g directions, so opposite directions to laser beams. The sigma plus, sigma minus. Okay, laser beams will drive delta m plus minus transition because they propagate in opposite directions. Okay. The sigma minus beam, this beam, is close to resonance for an atom with the positive g coordinate than the opposing sigma plus at beam. So sigma minus beam is close to the resonance for atom here. Okay. So the positive g coordinate and this position. Okay, so the atom therefore scatters more sigma minus than sigma plus photons and is pushed back towards g equals 0. So this atom at this atom in this position are influenced by sigma minus more than sigma plus. So to the interaction, this atom push back to z equals 0. Okay. On the other hand, for an atom in the negative g coordinate at this position, the scattering of sigma plus photons these photons is stronger, so it is pushed back to equal 0. So in this way, atoms can be trapped at the center of this position. Okay. So that is the basic principle of the marked optic trap. Now let's see the subrecoil cooling. If an atom observes a resonant photon, the atom will move in photon's direction. We already discussed this one. As a result, the atom gains momentum, this momentum. The equation for the equivalent energy is given by this equation. The single photon recoil temperature limit is what results if this energy is converted to temperature. This temperature for natrium atoms is approximately 1 Kelvin. So this was already discussed in the previous slide. By observing the laser photon with the frequency omega, the atoms in the lower energy state E1 can transition to higher state E2 equal E1 plus H1 omega. The atom can still spontaneously transition to a third state E3 by emitting a photon with a different frequency. Because there are no photons with a resonance frequency needed for a transition to a different level, the atoms in the energy level E3 are no longer interacting with the laser. Even though transitions from this state are possible in principle, the term dark state is often used to refer to a state that is inaccessible by the specific laser used. Two circularly polarized laser beams traveling in opposite directions are superimposed on the atom to induce their transition to the dark state. Since there are no laser photons available for the transition to other state, the atoms cannot leave dark state once they have entered it. Okay. Coherent population trapping is the process by which a system of atoms becomes inevitably trapped coherently in dark state as a result of decay into it over time. VSCPT, velocity selective coherent population trapping, is the name of this method. Using the VSCPT technique, normal group cool down the one-dimensional helium atoms to 2 microkelvin. That is half of the record temperature limit in 1988. In 1992, they also achieved the cooling to 250 nanokelvin and 180 nanokelvin for helium atoms in 2 and 3 dimensions respectively. This figure shows the dark state. The atoms in E3 here remain there since there isn't an appropriate laser photon needed for them to transition to some other state. So the atoms should stay here because there is no laser beam needed for transition to other states. So we call this state the dark state. As illustrated in the figure, this temperature corresponds to an atom speed of around 2 centimeters per second, this one. 250 nanokelvin. We can make an atomic watch that this figure shows speed distribution of helium atoms at 180 nanokelvin. This corresponds to the distribution of the speed of atoms. So this atom's speed corresponds to about 2 centimeters per second. Almost a trapping. So no movement, slight movement, right? 2 centimeters per second movement. So that corresponds to the temperature of 180 nanokelvin. We can make an atomic watch that is 100 times more accurate than the present one if we use laser cooling. As a result, more precise gravitational measurement will be achievable using this laser cooling method.